Max Planck stands as one of the towering figures in the history of science, known primarily for his groundbreaking work in the field of quantum mechanics. His legacy is anchored in the formulation of the Planck constant, a discovery that would go on to reshape the very fabric of physics. Yet, while his name is etched in the annals of scientific achievement, the depth of his contributions often goes beyond the confines of what is widely acknowledged. To understand Planck's legacy is to understand not only the birth of quantum theory, but also the complex nature of scientific discovery itself, marked by personal struggles, intellectual revolutions, and a shift in how humanity perceives the very nature of reality. Born in 1858 inches, the heart of Germany, Max Planck was raised in a family steeped in academic tradition. His father, a professor of law, ensured that young Max was surrounded by an environment that fostered intellectual curiosity. However, it was not the world of law that intrigued him, but rather the mysteries of nature that lay hidden in the realm of physics. Planck's early academic career was shaped by his studies in Munich and Berlin, where he quickly rose to prominence as a brilliant young physicist. By the late 19th century, the scientific community had already witnessed a tremendous leap in understanding the natural world, but the mysteries surrounding the nature of light and energy still loomed large. The prevailing theories of the time, particularly those of classical mechanics and thermodynamics, seemed to explain the behavior of matter and energy quite well, but there was one major flaw. These classical theories failed to explain the peculiar behaviors exhibited by radiation emitted from heated objects, phenomena that appeared to contradict the established rules of physics. In essence, while classical theories could explain the behavior of objects in most situations, they could not account for the strange observations made in the realm of heat and light. This was known as the ultraviolet catastrophe, a problem that troubled some of the best minds of the era, including Albert Einstein and Lord Rayleigh. It was in the midst of this intellectual crisis that Max Planck would emerge as a key player in one of the most pivotal moments in scientific history. The quest to solve the ultraviolet catastrophe was Planck's defining challenge. In 1900, as part of his efforts to solve the problem, Planck developed what would later become known as the Planck radiation law. This was a mathematical formulation that successfully explained the distribution of radiation emitted by a blackbody at different temperatures. Planck's approach was revolutionary because it incorporated a novel concept: energy could only be emitted or absorbed in discrete units, or quanta. This was a radical departure from the continuous nature of energy that had been assumed by classical physics. The introduction of quanta was, in fact, the birth of quantum theory. However, Planck himself was reluctant to embrace the full implications of his discovery. While his radiation law solved the immediate problem of the ultraviolet catastrophe, Planck saw his theory primarily as a mathematical convenience, not a fundamental rethinking of the nature of energy. His initial discomfort with the concept of quanta reflects a common theme in scientific discovery: a scientist's reluctance to abandon established paradigms, even when confronted with evidence that contradicts them. Planck was a deeply committed believer in the principles of classical physics, and the idea of energy being quantized seemed counterintuitive to everything he had learned. This tension between his intellectual commitments and the consequences of his discovery is what makes Planck's contribution to quantum theory so fascinating. He was, in many ways, a reluctant revolutionary. While his equations and mathematical models paved the way for the development of quantum mechanics, Planck himself remained somewhat wary of the broader philosophical implications. Unlike later proponents of quantum theory, such as Albert Einstein and Niels Bohr, who embraced the idea of a quantum world with enthusiasm, Planck's attitude was one of cautious acceptance. He viewed the quanta as a mathematical abstraction that could be used to explain experimental data, but he did not fully believe in the profound philosophical changes that the quantum worldview would eventually bring. This hesitation to fully embrace the quantum revolution may seem unusual, given that it was Planck's own discovery that opened the door to the quantum world. Yet, it speaks to a deeper issue in the nature of scientific progress. Even the greatest minds can be hesitant to let go of old ideas. Planck's struggles mirror the experiences of other scientists who have made discoveries that shook the foundations of their fields. Even though Planck had pioneered the path to quantum mechanics, he did not immediately accept its radical nature. His journey reflects the delicate balance between intellectual curiosity, personal belief, and the evolving nature of scientific understanding. In the context of Planck's legacy, his early reluctance to embrace the full implications of his theory should not detract from the magnitude of his achievement. On the contrary, it serves to highlight just how profound and unsettling his discovery was. It was a fundamental shift in how we understood energy and matter, one that required a complete rethinking of the laws of physics. While Planck's colleagues, such as Albert Einstein, would go on to fully embrace the quantum revolution, Planck remained in the shadows of the emerging quantum world, hesitant but still guiding the way. One of the key elements that distinguished Planck from his contemporaries was his commitment to bridging the gap between classical and modern physics. Throughout his career, Planck worked tirelessly to maintain coherence between the traditional, deterministic laws of physics and the nascent, probabilistic principles of quantum theory. This desire to reconcile the old and the new reflected a deep intellectual conservatism that was rooted in his respect for the foundational principles of science. But it also created a tension between his adherence to classical views and the revolutionary changes unfolding in the scientific community. While Planck's reluctance to embrace the full implications of quantum theory might be seen as a limitation, it is important to understand that it was not for lack of insight or understanding. Planck was one of the most brilliant minds of his generation, and he understood the mathematical and physical significance of his discoveries. His hesitance came from a place of intellectual integrity. He was unwilling to leap to conclusions that might undermine the very foundations of physics that he had spent his life studying. In this sense, Planck's work is a reminder that scientific progress often unfolds in fits and starts, with revolutionary discoveries often being tempered by the caution of the scientist who made them. Despite his hesitations, the consequences of Planck's discovery were far-reaching. The quanta, which he had introduced as a mathematical tool, became the cornerstone of quantum mechanics, a theory that would eventually lead to the development of technologies that have changed the world, everything from computers and semiconductors to lasers and quantum computing. However, for Planck, these were not immediate concerns. His focus remained on the immediate problem at hand, the ultraviolet catastrophe. It was only later, as the implications of his work began to sink in, that Planck would come to realize the true magnitude of what he had uncovered. In retrospect, Planck's cautious approach to his own discovery can be seen as a testament to his scientific rigor. While other scientists, particularly those in the quantum camp, embraced the new theory with enthusiasm, Planck maintained a cautious distance. He wanted to ensure that his work was grounded in a firm scientific foundation, and this restraint only added to the depth and richness of his legacy. His discovery, though reluctantly accepted by its creator, opened the door to a new era of scientific exploration, one that would forever change the way we understand the universe. In conclusion, Max Planck's role in the development of quantum mechanics cannot be overstated. His discovery of the Planck constant and the introduction of quanta were revolutionary in every sense of the word. Yet, Planck's personal struggle to reconcile his discovery with the classical physics he had spent his career defending speaks to the complexity of scientific progress. Planck's work did not just change the course of physics, it challenged the very way we think about the nature of reality itself. The secret discovery that Max Planck hid from us, therefore, is not just the idea of quanta, but the profound shift in perspective that it represents, a shift that Planck himself was not fully ready to embrace, but one that would ultimately transform the world. Max Planck's contributions to the world of physics are not only monumental in the context of quantum theory, but also offer a fascinating study in the dynamics of intellectual resistance and acceptance. While the first part of Planck's work established the foundation for what would later become quantum mechanics, it is his personal hesitancy and reluctance to fully embrace the implications of his own discoveries that adds depth to his legacy. Planck, a man of great intellectual rigor, was not one to easily relinquish his faith in classical physics, a domain he had spent most of his career contributing to. His discovery, which would eventually transform the way we perceive energy, light, and matter, was initially not something he felt fully comfortable with. This internal conflict is an often overlooked aspect of Planck's genius, revealing how even the greatest scientists face moments of intellectual doubt and transformation. The Planck constant, a key element of Planck's work, would go on to play an instrumental role in the development of quantum mechanics. However, despite its mathematical elegance and the way it explained the distribution of blackbody radiation, Planck himself was reluctant to accept the revolutionary implications of the quantum nature of energy. Unlike other key figures in the development of quantum theory, such as Albert Einstein, Niels Bohr, and Werner Heisenberg, Planck did not immediately adopt the idea that nature itself operated on discrete units of energy. Instead, he viewed quanta as a temporary mathematical tool designed to explain experimental data that classical physics could not. This reluctance to accept quantum theory was not a matter of ignorance or lack of understanding. Planck was fully aware of the significance of his discovery, but he was also deeply committed to the laws of classical physics. Classical mechanics, based on the principles of Newton and Maxwell, had served as the foundation of modern physics for centuries, providing a coherent and reliable framework for understanding the natural world. For Planck, the idea that energy could be quantized was a deeply unsettling concept. It went against everything he had learned and believed about the continuity of energy in the physical world. At the heart of Planck's hesitation was his belief that the quantum nature of energy was merely a mathematical artifact, a tool that worked to explain the problems associated with blackbody radiation, but not a true reflection of the fundamental nature of reality. Planck even attempted to temper the implications of his discovery by suggesting that the concept of quanta was only a temporary fix, a mere hypothesis to solve a specific problem in physics. This is in stark contrast to the way the quantum world would later be understood by others, who would embrace its principles as a new way of understanding reality itself. One of the key reasons for Planck's reluctance to fully embrace quantum theory was his commitment to determinism, the idea that every physical event could be predicted if the initial conditions were known. Classical physics, with its reliance on continuous quantities, fit neatly within a deterministic framework. The idea that energy could exist only in discrete units seemed to challenge this deterministic view, introducing an element of randomness and uncertainty that was foreign to Planck's understanding of the universe. For him, the implications of quantum theory were not just mathematically uncomfortable, they represented a profound philosophical shift that he was not ready to accept. While Planck struggled with the philosophical implications of his own discovery, it is important to recognize that he never abandoned his pursuit of scientific truth. Even if he did not fully embrace the implications of quantum mechanics, his work still laid the foundation for future developments in the field. The Planck constant, which was at the heart of his radiation law, would become one of the cornerstones of quantum theory, used by Einstein in his explanation of the photoelectric effect and later by Heisenberg, Bohr, and Schrödinger in their development of quantum mechanics. Planck's unwillingness to accept the radical nature of his discovery did not diminish its importance or its impact on the scientific world. In fact, it may have even enhanced the legacy of his work, adding an element of complexity and mystery that continues to intrigue physicists today. As the 20th century unfolded, the scientific community began to embrace the new quantum worldview. Pioneers like Einstein, Bohr, and Heisenberg made major strides in developing the theory, but even they faced challenges in reconciling it with the classical view of physics. The uncertainty principle, wave-particle duality, and the idea of quantum entanglement all emerged as central tenets of quantum theory, further distancing it from the determinism and continuity that had defined classical physics. For many scientists, the shift to quantum mechanics was both exhilarating and unsettling, as it forced them to rethink not just the nature of energy and matter, but the very nature of reality itself. For Planck, however, this shift was not one he could easily make. His internal struggle reflects a broader tension within the scientific community, the conflict between embracing new, revolutionary ideas and holding on to old paradigms that had served science well for centuries. Planck's reluctance to fully embrace quantum mechanics is not a reflection of his lack of insight, but rather a testament to the deep intellectual conservatism that often accompanies scientific breakthroughs. It takes time for new ideas to be fully accepted, and sometimes even the pioneers of those ideas are the last to see their full implications. Despite his personal hesitance, Planck's legacy is one of immense importance. His work in developing the theory of blackbody radiation and introducing the concept of quanta laid the foundation for the quantum revolution that would follow. Planck's influence can be seen in the work of Einstein, Bohr, Heisenberg, and others who would push the boundaries of physics even further. His contributions to quantum theory opened the door for the development of technologies that have had a profound impact on the modern world, from the invention of the transistor and the development of computers to the advent of quantum computing and quantum cryptography. The story of Max Planck is, in many ways, the story of scientific discovery itself, an unfolding process of revelation, resistance, and eventual acceptance. His legacy serves as a reminder that even the most transformative ideas in science are often met with skepticism and reluctance. Planck's story also highlights the personal dimension of scientific discovery, the struggles and doubts that even the greatest minds experience as they confront the implications of their work. His journey through the quantum revolution is a testament to the power of intellectual curiosity and the courage it takes to pursue truth, even when it leads to uncharted territories. In the end, Planck's discovery was not just about introducing a new scientific theory, but about redefining the very way we understand the universe. His work prompted a paradigm shift that would shape the future of physics for generations to come. While Planck himself may have been hesitant to fully embrace the quantum revolution, his contributions were indispensable in bringing about the scientific revolution that would change the world. The secret discovery that Max Planck hid from us, in many ways, is not the quantum nature of energy itself, but the quiet, intellectual struggle that preceded it, a struggle that continues to resonate in the work of scientists today, as they push the boundaries of what we know and strive to unlock the mysteries of the universe. Max Planck's discovery of quantum theory is one of the most significant milestones in the history of physics, marking a profound shift in our understanding of the natural world. His work on blackbody radiation and the concept of quanta fundamentally changed the way scientists perceive energy and matter. Yet, to truly appreciate the significance of Planck's contributions, it is essential to understand not just the discovery itself, but the intellectual climate of the time, the challenges that Planck faced, and the broader implications of his findings. At the heart of Planck's success lies the moment when he bridged the gap between classical mechanics and the emerging quantum reality, a leap that would later give birth to the field of quantum mechanics. However, Planck's personal struggle with his own discovery presents a fascinating aspect of his legacy, as he was initially hesitant to embrace the full consequences of his work. In this documentary-style exploration, we will look at how the birth of quantum theory was driven by the intellectual forces of its time, and Planck's pivotal role in laying the foundation for what would become one of the most transformative shifts in the history of science. Planck's work on blackbody radiation began in the late 19th century when physicists faced a significant problem in understanding the behavior of radiation emitted by heated objects. Classical physics, with its reliance on the laws of thermodynamics and electromagnetism, could not explain why objects heated to high temperatures emitted radiation in such a peculiar way. According to classical physics, the intensity of radiation should increase indefinitely as the temperature of an object rises, particularly in the ultraviolet range. This discrepancy, known as the ultraviolet catastrophe, was one of the most pressing issues in physics at the time. A major breakthrough was required, and it was this challenge that led Planck to formulate his own solution, which would ultimately redefine the field of physics. At the heart of Planck's approach was a simple yet radical idea. Energy could not be emitted or absorbed in continuous amounts, as classical physics had assumed. Instead, energy came in discrete packets, which Planck referred to as quanta. This was an audacious concept because it directly contradicted the established belief that energy was continuous. For many years, the scientific community had accepted that energy could be divided infinitely, a concept that seemed logical given the laws of classical mechanics. But Planck's insight was to treat energy as quantized, a series of discrete levels that could be measured and calculated. His formulation, known as the Planck radiation law, successfully explained the distribution of radiation emitted by a blackbody and resolved the ultraviolet catastrophe that had baffled scientists for decades. What made Planck's approach truly revolutionary was the introduction of the Planck constant, denoted as h, a physical constant that represented the smallest possible unit of energy. This constant would later become one of the foundational pillars of quantum mechanics. The Planck constant was central to Planck's mathematical model, as it related the energy of a quantum to the frequency of the radiation being emitted. This relationship not only solved the problem of blackbody radiation, but also introduced a new way of thinking about energy, one that would lay the groundwork for the development of quantum theory. However, despite the success of his work, Planck's own reaction to his discovery was more subdued than one might expect from a scientist who had just unlocked one of the greatest mysteries of the universe. For Planck, the idea of quanta was not an immediate breakthrough in the way we understand modern physics today. While his formula was mathematically elegant and effective in solving the blackbody radiation problem, Planck viewed the concept of energy quanta as a temporary fix rather than a permanent shift in the understanding of energy. In fact, he believed that his theory was merely a mathematical convenience, something that worked well to explain the data, but not a fundamental change in how energy functioned in the physical world. Planck himself was deeply rooted in classical physics, and the idea that energy could be discrete rather than continuous was difficult for him to accept on a deeper philosophical level. Despite the revolutionary nature of his discovery, Planck did not initially believe that it would lead to the birth of a new field of physics. He did not see it as the opening door to the strange and paradoxical world of quantum mechanics that would eventually take shape in the hands of Einstein, Bohr, Heisenberg, and others. Planck's reluctance to fully embrace his own discovery stems from the intellectual conservatism that characterized his approach to science. He was a product of the late 19th century scientific tradition, one that was committed to the idea that the natural world operated according to deterministic laws. Classical physics, based on the works of Newton and Maxwell, had provided a coherent and unified understanding of the physical universe. For Planck, the continuous nature of energy had been an essential feature of classical mechanics, and the notion that energy could be broken into discrete units threatened to undermine the very foundation of this worldview. Even as he recognized the validity of his radiation law, Planck clung to the idea that his quanta were merely a mathematical convenience and not a true reflection of the underlying nature of reality. This intellectual struggle was not unique to Planck. Throughout the history of science, many great discoveries have been met with initial resistance as scientists grapple with the implications of their work. Planck's hesitation to fully accept the quantum nature of energy is an example of how deeply entrenched ideas can be, even in the face of groundbreaking evidence. It was only later, as the implications of his work began to sink in, and as others, such as Einstein, embraced the quantum revolution with greater enthusiasm, that Planck began to recognize the full scope of his contributions. In fact, Planck would later refer to his discovery of quanta as one of the most important developments in his life, although he continued to hold reservations about the broader implications of the quantum worldview. Planck's contribution to quantum theory cannot be overstated. His introduction of energy quanta and the Planck constant was the first step in the creation of a new scientific paradigm. However, the quantum revolution did not occur in a vacuum. It was the result of decades of work by a community of scientists who, building on Planck's foundation, would go on to uncover the strange and counterintuitive properties of the quantum world. Albert Einstein, who was influenced by Planck's work, took the next step by applying the concept of quanta to explain the photoelectric effect, further solidifying the role of quantum theory in the broader understanding of light and energy. Meanwhile, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger expanded on these ideas to develop the full framework of quantum mechanics, which would challenge everything previously understood about the behavior of particles, energy, and the fabric of reality itself. Despite the broader acceptance of quantum mechanics in the scientific community, Planck remained somewhat ambivalent about the theory throughout his life. He continued to defend classical ideas and remained wary of the philosophical implications of quantum mechanics. While he recognized the power and utility of the quantum model, Planck was hesitant to fully accept its revolutionary nature, especially its departure from classical determinism. This reluctance reflects a deeper tension between the known and the unknown, the comfortable and the unknown, a tension that often defines the personal experiences of groundbreaking scientists as they push the boundaries of human knowledge. In the case of Planck, the discovery of quantum theory was a profound leap forward, but it was also a moment of personal conflict as he struggled to reconcile the new with the old. In conclusion, Max Planck's work on quantum theory represents one of the most significant intellectual shifts in the history of science. His introduction of the Planck constant and the concept of energy quanta laid the groundwork for the development of quantum mechanics. However, Planck's own reluctance to fully embrace the implications of his discovery provides a fascinating layer to his legacy. His struggle to accept the true nature of his work speaks to the broader challenge of scientific discovery, the tension between established knowledge and revolutionary new ideas. Even as Planck bridged the gap between classical and quantum physics, he remained cautious, unwilling to fully embrace the radical shift that he had set into motion. It is this complexity, this internal struggle, that makes Planck's contribution to science so compelling and his legacy so enduring. Max Planck's discovery of quantum theory, though initially seen as a mathematical convenience, evolved into one of the most profound and transformative shifts in the history of science. While his work on blackbody radiation and the introduction of energy quanta solved a major puzzle in physics, it also opened up an entirely new domain of understanding quantum mechanics. However, the personal and intellectual journey Planck embarked on, particularly his reluctance to fully accept the far-reaching implications of his own discoveries, offers an intriguing perspective on how revolutionary science is often met with skepticism, even by its creators. The period in which Planck worked was a time of great intellectual upheaval. The classical laws of physics, such as those developed by Isaac Newton and James Clerk Maxwell, had been immensely successful in explaining the macroscopic world. These laws govern the motions of planets, the behavior of gases, and the propagation of electromagnetic waves. Yet, as scientists delved deeper into the microscopic world, they encountered phenomena that classical physics could not explain. Among these, the behavior of radiation emitted by heated objects, specifically the way the radiation intensity increased at certain wavelengths, was one of the most perplexing. The ultraviolet catastrophe, as it was called, occurred when the predictions made by classical physics about blackbody radiation were compared to experimental results. Classical theory predicted that the intensity of radiation emitted by a blackbody, an idealized object that absorbs all incoming radiation, would increase infinitely as the wavelength decreased, particularly in the ultraviolet range. This contradiction between theory and experiment pointed to the limitations of classical physics, and physicists were at a loss for how to reconcile the two. It was in the midst of this crisis that Planck made his breakthrough. By 1900, after much work on the subject, Planck formulated what became known as the Planck radiation law. This law accurately described the radiation emitted by a blackbody at various temperatures and solved the ultraviolet catastrophe. The key to Planck's solution was the idea that energy is quantized. Energy is not emitted or absorbed continuously, as classical physics had assumed, but in discrete packets or quanta. This concept, introduced through the Planck constant, marked the birth of quantum theory. The beauty of Planck's formula was that it not only matched experimental data, but also paved the way for future developments in physics. However, Planck did not immediately realize the full implications of his discovery. Initially, he saw the quantization of energy as a mere mathematical device, a way of resolving a particular problem in radiation theory, rather than a new and fundamental understanding of the nature of energy itself. For Planck, this was simply a tool to fix an anomaly in classical physics, not the foundation for an entirely new framework of understanding the universe. The idea of quantized energy, while mathematically effective, seemed at odds with the classical view of a continuous and deterministic world. This hesitation is understandable, considering the intellectual environment of the time. Classical physics was deeply ingrained in the scientific community, and most physicists adhered to the belief that energy, like other physical quantities, was continuous and could be divided into infinite smaller parts. The concept of quantization, which Planck introduced, contradicted this notion. It suggested that energy could only exist in specific, discrete amounts. For a scientist like Planck, who had spent much of his career working within the classical framework, accepting such a radical idea was not easy. The quantization of energy was not just a mathematical concept, but a challenge to the very principles of determinism and continuity that had defined classical physics for centuries. Despite his initial reluctance, Planck's discovery laid the foundation for what would become one of the most profound revolutions in science. The quantization of energy became a key element in the development of quantum mechanics, a theory that would reshape our understanding of the fundamental nature of reality. Albert Einstein, building on Planck's ideas, would later use the concept of quanta to explain the photoelectric effect, a discovery that earned him the Nobel Prize in Physics in 1921 and further solidified the importance of Planck's work. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, among others, would extend Planck's ideas to form a complete theory of quantum mechanics, a theory that describes the behavior of particles at the smallest scales. While Planck's work laid the groundwork for quantum theory, it was his reluctance to fully embrace the implications of his own discovery that adds a unique dimension to his legacy. Planck was, by all accounts, a deeply cautious and conservative scientist. He believed in the power of classical physics and the deterministic laws that governed the universe. The idea that energy was quantized challenged the very principles he had spent much of his life defending. For this reason, Planck continued to hold on to classical views for as long as possible. even as his work began to point the way toward a radically different understanding of the physical world. This internal struggle between classical and quantum physics was not unique to Planck. Many of the early pioneers of quantum theory, including Einstein and Bohr, faced similar conflicts. Einstein, for example, initially resisted the probabilistic nature of quantum mechanics, famously saying, "God does not play dice with the universe." It was only over time, as more experimental evidence supported the validity of quantum theory, that Einstein and others came to accept its full implications. Planck's hesitation, therefore, reflects a broader theme in the history of science: the reluctance of scientists to let go of old ideas in favor of new, revolutionary ones. This tension between the known and the unknown is a constant in the progression of scientific knowledge. Even as he continued to champion the validity of quantum theory, Planck remained somewhat uncomfortable with the deeper philosophical implications of the quantum world. He never fully embraced the probabilistic nature of quantum mechanics, which contradicted the deterministic worldview of classical physics. For Planck, the quantum world remained a theoretical construct, useful for explaining experimental results, but not necessarily a true reflection of the underlying reality of the universe. This perspective placed him at odds with the likes of Bohr, who was more willing to accept the strange and counterintuitive nature of quantum mechanics. Planck's reluctance to fully embrace the quantum revolution speaks to the complexity of scientific progress. Great discoveries often come with a mix of excitement, fear, and uncertainty. While Planck's mathematical models and equations were the starting point for a new era in physics, his personal journey reflects the challenges scientists face when confronted with ideas that fundamentally change how we understand the world. The quantum theory that Planck helped to create was not just a technical breakthrough, it was a paradigm shift, one that forced scientists to rethink the very nature of reality. In the years following his initial discovery, Planck would come to realize that the implications of his work were far more profound than he had originally imagined. Though he never fully embraced the quantum worldview in the way that Bohr or Einstein did, Planck's influence on the development of quantum mechanics is undeniable. His work opened the door for the next generation of physicists to build upon and ultimately replace classical physics with a new theory that could explain the behavior of particles on the smallest scales. His discovery of the Planck constant remains one of the most important constants in physics, providing a foundation for fields ranging from quantum computing to quantum cryptography. The story of Planck's contribution to quantum theory is one of intellectual conflict, resistance, and eventual acceptance. His work solved one of the most pressing problems in physics, yet the personal journey he underwent, his reluctance to fully embrace the quantum nature of energy, adds a layer of complexity to his legacy. Planck's story is a reminder that even the most groundbreaking discoveries are not always immediately understood or accepted by the scientists who make them. It is only through time, further experimentation, and the contributions of future generations that the true significance of such discoveries becomes clear. Planck's legacy, though tinged with personal hesitation, remains a cornerstone of modern physics, a testament to the power of intellectual curiosity and the courage to explore the unknown. Max Planck's journey through the development of quantum theory is not just the story of a scientific breakthrough, but also an exploration of the complexities, hesitations, and eventual triumphs that characterize the process of scientific discovery. As one of the founding figures of modern physics, Planck's work, particularly his introduction of the Planck constant and the concept of quantized energy, laid the foundation for a revolution in our understanding of the universe. However, to fully appreciate the significance of his contributions, it is essential to understand the broader context in which Planck operated, the intellectual struggles he faced, and the legacy of his discoveries. At the end of the 19th century, the field of physics stood at a crossroads. The classical physics of Newton, Maxwell, and others had been remarkably successful in explaining the behavior of large-scale phenomena. The laws of motion and electromagnetism had provided a coherent framework for understanding the universe at a macroscopic level. However, when scientists began to investigate the behavior of radiation emitted by heated objects, they encountered a paradox that could not be explained by classical physics. This paradox, known as the ultraviolet catastrophe, arose when classical theories predicted that the intensity of radiation would increase indefinitely as the wavelength decreased, particularly in the ultraviolet range. Experimental data, however, showed that this was not the case, and this contradiction between theory and observation presented one of the most significant challenges in physics at the time. Enter Max Planck, a German physicist who, in 1900, would provide the first breakthrough in solving this problem. Planck's solution was both simple and radical. He proposed that energy, rather than being continuous as classical physics assumed, is emitted in discrete packets, which he called quanta. This was an astonishing departure from the classical view of energy as a continuous, divisible substance. Planck's hypothesis was mathematically elegant, but it was also conceptually troubling, as it directly contradicted centuries of scientific thinking. At the time, energy was viewed as a smooth, continuous flow, much like water flowing from a tap. The idea that energy could only exist in discrete amounts, like individual drops, was a challenging concept to accept, even for Planck himself. Planck's introduction of the concept of quanta represented the first step in the birth of quantum mechanics. The Planck constant, a fundamental physical constant, emerged from his work as a way to quantify the relationship between the energy of a quantum and the frequency of radiation. This constant would later become one of the pillars of quantum theory. However, despite the success of his mathematical model, Planck's own understanding of the quantum nature of energy was initially limited. He did not view his discovery as a permanent departure from classical physics, but rather as a mathematical convenience, a temporary fix for the problem of blackbody radiation. At first, Planck did not fully grasp the philosophical implications of his work. While his formula solved the immediate problem of blackbody radiation and matched experimental data, he remained deeply rooted in the classical worldview. Planck was a conservative scientist, deeply attached to the deterministic principles of classical physics. The idea that energy could be quantized seemed to contradict everything he had learned about the smooth, continuous nature of the physical world. This intellectual tension, the reluctance to embrace a radical shift in understanding, became a central theme in Planck's relationship with his own discovery. In contrast to Planck's cautious attitude, other physicists, particularly Albert Einstein, were more willing to embrace the new quantum reality. Einstein's work on the photoelectric effect in 1905 provided further confirmation of the idea of quanta. By explaining the emission of electrons from a metal surface when illuminated by light as a result of discrete packets of energy, photons, Einstein helped to solidify the idea of quantized light, a concept that had profound implications for the understanding of energy and matter. However, even Einstein, who fully embraced the quantum nature of light, had reservations about the broader implications of quantum theory, particularly its probabilistic nature. The probabilistic interpretation of quantum mechanics, which emerged later through the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, was a far cry from the deterministic worldview that had governed classical physics for centuries. Planck's discomfort with the implications of quantum theory was not unique to him. Many of the early pioneers of quantum mechanics, including Bohr and Heisenberg, faced a similar struggle. The shift from a deterministic to a probabilistic view of the universe was not only intellectually unsettling but also philosophically challenging. The classical world was governed by clear, predictable laws, where the future of a system could, in principle, be determined from its initial conditions. In the quantum world, however, uncertainty and probability replaced certainty and determinism. The idea that particles could exist in multiple states simultaneously, or that the act of measurement could alter the state of a system, was profoundly unsettling to many scientists. Planck himself remained attached to the classical view of the universe, even as he acknowledged the mathematical validity of quantum theory. One of the most striking aspects of Planck's relationship with his discovery is the contrast between the groundbreaking nature of his work and his personal reluctance to fully embrace its implications. Planck was not alone in this regard. Many scientists struggle with the philosophical consequences of their discoveries. In the case of quantum theory, the implications were particularly profound, as they challenged the very foundations of how humans understand reality. The idea that the universe, at its most fundamental level, is governed by principles of uncertainty and probability, rather than determinism, represents a radical departure from centuries of scientific tradition. Planck's personal hesitation serves as a reminder of how difficult it can be for even the greatest minds to let go of established ways of thinking. Despite his initial reluctance, Planck's contributions to quantum mechanics were immeasurable. His work on blackbody radiation and the introduction of energy quanta laid the foundation for the development of quantum theory, which would go on to revolutionize physics. Quantum mechanics not only explains the behavior of particles at the smallest scales, but also has practical applications in technologies such as semiconductors, lasers, and quantum computing. Planck's work was the first step in the creation of a new framework of physics, one that has transformed not only how scientists understand the microscopic world, but also how we understand the nature of reality itself. Planck's legacy is not just in the technical aspects of his discoveries, but also in his role as a bridge between the old and the new. His work marked the end of an era in physics and the beginning of a new one that embraced uncertainty and probabilistic laws rather than determinism. While Planck was reluctant to fully embrace the implications of his own discovery, his work set in motion a chain of events that would forever change the way we view the universe. The quantum revolution, which Planck inadvertently helped to usher in, continues to shape the course of physics and technology today. In conclusion, Max Planck's role in the birth of quantum mechanics represents both a scientific breakthrough and an intellectual journey fraught with resistance and self-doubt. His work on the quantization of energy was the key to unlocking the mysteries of blackbody radiation and laid the foundation for quantum theory. However, Planck's reluctance to fully embrace the implications of his discovery speaks to the broader challenges of scientific progress. His story is a reminder that revolutionary ideas often come with intellectual and philosophical struggles, even for the greatest scientists. Planck's work not only changed the course of physics, but also challenged our understanding of the very nature of reality. Though he may not have fully embraced the quantum world in the way that others did, his contributions remain a cornerstone of modern physics and continue to influence the field today. Max Planck's role in the development of quantum theory remains one of the most important turning points in the history of science. The introduction of the Planck constant and the concept of energy quantization would eventually form the foundation for the entire field of quantum mechanics, which radically transformed our understanding of the universe at the microscopic level. But to truly appreciate the significance of Planck's contributions, it is important to consider not just the scientific breakthroughs he made, but also the intellectual and emotional journey that accompanied them. Planck's reluctance to fully accept the implications of his own discoveries, his complex relationship with the emerging quantum theory, and the eventual impact of his work are all part of the story that would forever change the trajectory of modern physics. One of the key elements of Planck's discovery was the way it resolved the ultraviolet catastrophe, a critical problem in the field of thermodynamics and classical physics at the turn of the 20th century. Classical physics, particularly the laws of thermodynamics and electromagnetic theory, developed by figures such as Maxwell, had successfully explained much of the behavior of matter and energy on a macroscopic scale. However, when scientists turned their attention to the behavior of radiation emitted by heated objects, specifically blackbodies, idealized objects that absorb and emit radiation perfectly, they encountered a fundamental flaw in their understanding. Classical theories predicted that the intensity of radiation would increase without bound as the wavelength of the emitted radiation shortened, especially in the ultraviolet range. But experimental data showed that radiation intensity actually leveled off at shorter wavelengths, creating a discrepancy that became known as the ultraviolet catastrophe. Planck's breakthrough came when he proposed a solution that involved the quantization of energy. He postulated that energy is not emitted or absorbed continuously, as classical physics had assumed, but in discrete packets, or quanta. The energy of these quanta was proportional to the frequency of the radiation, with Planck introducing a new constant, later known as the Planck constant, to describe the relationship between energy and frequency. This simple yet radical concept provided an elegant mathematical solution to the problem of blackbody radiation and allowed Planck's radiation law to match experimental results perfectly. This was a groundbreaking moment in physics, as it represented the first clear evidence that energy could be quantized, a notion that would become the cornerstone of quantum theory. Yet, despite the mathematical success of his theory, Planck himself struggled to embrace the full implications of his discovery. In many ways, Planck was a man caught between two worlds: the old, classical physics that he had grown up with, and the new, emerging quantum reality that his own work had helped to create. His introduction of the concept of quanta was not immediately embraced as a fundamental shift in understanding the nature of energy. Instead, Planck himself viewed it as a mathematical tool, something that worked to explain the experimental data, but not necessarily a reflection of the true, underlying nature of the universe. For Planck, the notion of quantized energy seemed more like a temporary fix, a stopgap measure to resolve the issue of blackbody radiation, rather than a profound new way of thinking about reality. Planck's reluctance to fully accept the quantum nature of energy reflects a broader tension within the scientific community at the time. Classical physics, which had been so successful in explaining macroscopic phenomena, was built on the idea that the universe operated according to deterministic laws. The idea of discrete energy packets, on the other hand, suggested a universe that was probabilistic and uncertain. This new quantum reality threatened to unravel the deterministic worldview that had been so central to classical physics. Planck, who had spent much of his career studying and working within the classical framework, was understandably hesitant to embrace such a radical departure from the principles that had guided his understanding of the world. This reluctance was not unique to Planck. Many of the other pioneers of quantum theory, including Albert Einstein, Niels Bohr, and Werner Heisenberg, also faced significant challenges in accepting the full implications of quantum mechanics. For Einstein, the introduction of quanta to explain the photoelectric effect was a powerful confirmation of Planck's ideas, but it also created a philosophical conundrum. Einstein was famously uneasy with the probabilistic nature of quantum mechanics, famously remarking, "God does not play dice with the universe." His discomfort with the indeterminacy inherent in quantum theory would continue throughout his life, even as he made significant contributions to its development. Similarly, Niels Bohr, while one of the leading proponents of quantum mechanics, was also deeply conflicted about the implications of the theory. Bohr's development of the Bohr model of the atom was based on quantum ideas, but he continued to struggle with the philosophical implications of the theory, particularly the notion that particles could exist in multiple states at once and that their behavior could only be described probabilistically. For Bohr and many others, the shift to quantum mechanics represented a philosophical revolution that went beyond the boundaries of physics and challenged the very way humanity perceives the nature of reality. In contrast to Planck, who was initially reluctant to fully embrace the quantum nature of energy. Other scientists, such as Bohr and Heisenberg, were more willing to accept the strange and counterintuitive aspects of quantum mechanics. Heisenberg's uncertainty principle, for example, posited that it was impossible to simultaneously measure both the position and momentum of a particle with absolute precision, introducing an element of fundamental uncertainty into the description of physical systems. This was a direct challenge to the deterministic laws of classical physics, where such measurements were assumed to be both possible and predictable. Similarly, the concept of wave-particle duality, which emerged from the work of Louis de Broglie and others, suggested that particles could exhibit both wave-like and particle-like behavior depending on how they were observed. This duality was difficult for many scientists to accept, as it seemed to defy classical logic. Planck's own hesitation to fully embrace quantum theory can be seen as a reflection of the larger struggle within the scientific community. The shift from classical to quantum physics was not simply a matter of solving equations or developing new models. It required a profound change in how scientists thought about the nature of the universe. The classical world was one of certainty, where the future of a system could be predicted with precision if its current state was known. The quantum world, by contrast, was inherently uncertain and probabilistic, where outcomes could only be described in terms of probabilities. This shift from determinism to indeterminism was not just a scientific change, it was a philosophical and existential one, as it suggested that the universe was not as predictable or comprehensible as previously believed. Despite his initial reluctance, Planck's contributions to quantum mechanics were undeniable. His work laid the groundwork for the later developments of quantum theory, and his introduction of the Planck constant remains one of the cornerstones of modern physics. The mathematical elegance of Planck's radiation law and the concept of quanta provided the foundation for the quantum revolution that would unfold over the next few decades. As scientists like Einstein, Bohr, and Heisenberg pushed the boundaries of quantum theory, Planck's work served as the starting point for the development of a new physics that would ultimately revolutionize our understanding of the microscopic world. Planck's hesitation to embrace the full implications of his work also highlights an important aspect of scientific progress: the often slow and difficult process of paradigm shifts. Even the most groundbreaking discoveries are not immediately accepted or understood, even by the scientists who make them. Planck's reluctance to fully embrace quantum theory is a reminder that scientific progress is not always linear, and that the greatest discoveries often come with periods of doubt, resistance, and internal conflict. The history of quantum mechanics is full of such struggles, and Planck's story serves as an example of the intellectual and emotional journey that many scientists undergo when confronted with radical new ideas. In conclusion, Max Planck's contributions to quantum mechanics are among the most important in the history of science. His work on blackbody radiation and the introduction of energy quanta laid the foundation for the quantum revolution that would follow. However, his reluctance to fully embrace the implications of his own discovery reflects the broader intellectual challenges that come with revolutionary scientific ideas. Planck's story is not just one of scientific achievement, but also one of personal struggle and intellectual conflict. His work helped to reshape our understanding of the universe, but it also challenged the very foundations of classical physics. In the end, Planck's legacy is not just in the equations and constants he introduced, but in his role in ushering in a new era of physics, one that would forever change the way we perceive reality itself. Max Planck's contributions to science have shaped the course of modern physics, making him one of the most pivotal figures in the early 20th century. His work, particularly on blackbody radiation and the introduction of energy quanta, laid the foundation for quantum mechanics, a field that would fundamentally alter humanity's understanding of the universe. Yet, Planck's legacy is not simply about the equations he developed or the theories he proposed. His story is also one of intellectual struggle, personal doubt, and the resistance to embrace a revolutionary shift in how we perceive the nature of reality. At the heart of Planck's discovery lies his solution to the ultraviolet catastrophe, one of the most significant problems of the time. Classical physics, based on the work of Isaac Newton and James Clerk Maxwell, was highly successful at explaining large-scale phenomena, but struggled to explain the behavior of radiation emitted by heated objects. Specifically, the classical theory predicted that as the temperature of a blackbody, an idealized object that absorbs all radiation, increased, the intensity of radiation emitted would increase infinitely, particularly at shorter wavelengths, like ultraviolet. However, experimental data showed that radiation intensity did not increase infinitely, but rather peaked at a certain point and then decreased. This anomaly posed a severe challenge to classical physics, and no one knew how to reconcile these observations with established theories. Max Planck, in 1900, provided the first breakthrough in solving this problem. He proposed a radical idea. Energy could not be emitted or absorbed in a continuous manner, as classical physics had assumed. Instead, energy existed in discrete packets, or quanta. This was a revolutionary concept because it contradicted centuries of scientific thought that had held energy to be continuous. Planck's insight led to the formulation of the Planck radiation law, which successfully explained the distribution of radiation emitted by a blackbody and matched experimental observations. This discovery marked the birth of quantum theory, yet Planck himself did not immediately realize the profound implications of his work. Despite the success of his radiation law, Planck did not fully embrace the concept of quantized energy. He viewed the idea of quanta as a mathematical convenience, a way to solve a specific problem in radiation theory, rather than a new, fundamental way of understanding energy. In fact, Planck believed that his theory was a temporary solution, something that could be replaced by a more complete classical theory once the ultraviolet catastrophe was resolved. Planck's reluctance to fully accept the quantum nature of energy highlights the intellectual tension that existed between classical and emerging quantum physics. Planck was deeply embedded in classical physics, which was based on deterministic laws, and he had difficulty accepting the probabilistic and discontinuous nature of quantum theory. This intellectual struggle was not unique to Planck. Many other physicists who would later contribute to the development of quantum mechanics, including Albert Einstein and Niels Bohr, experienced similar doubts and conflicts. For instance, Einstein's work on the photoelectric effect confirmed Planck's ideas about the quantization of energy, yet he too struggled with the philosophical implications of quantum mechanics. Einstein famously rejected the probabilistic nature of quantum theory, stating, "God does not play dice with the universe." Bohr, on the other hand, fully embraced quantum mechanics and worked with Planck to develop the early quantum theory, but he, too, grappled with the paradoxes of the quantum world. The shift from classical to quantum physics represented not just a scientific revolution but a philosophical one, challenging long-held beliefs about the nature of reality. While Planck remained cautious about fully embracing the quantum worldview, his work was instrumental in laying the foundation for the quantum revolution that would unfold in the decades to come. His introduction of the Planck constant and the concept of quantized energy opened the door for later physicists, such as Einstein, Heisenberg, and Schrödinger, to develop quantum mechanics. The quantum theory, which emerged from Planck's initial discovery, revolutionized not just physics but also technology, enabling innovations such as semiconductors, lasers, and quantum computing. Planck's legacy, therefore, extends far beyond the immediate impact of his discovery. It also includes the ways in which his ideas set the stage for future scientific and technological advancements. In conclusion, Max Planck's work in developing quantum theory represents both a breakthrough in science and an example of the intellectual struggles that accompany great discoveries. His work on blackbody radiation and the concept of energy quanta laid the groundwork for the quantum revolution. However, Planck's reluctance to fully accept the implications of his own work speaks to the broader challenges of scientific progress. Great discoveries often come with resistance, doubt, and internal conflict, even from the scientists who make them. Planck's story, therefore, is not just one of scientific achievement, but also of intellectual courage and perseverance in the face of a paradigm-shifting discovery. His contributions to quantum mechanics will continue to shape the course of physics and our understanding of the universe for generations to come. Max Planck's name is synonymous with the birth of quantum mechanics, a revolutionary shift in the way humans perceive the physical world. His contributions to science were not merely mathematical, but were part of a deep intellectual journey that transformed the very fabric of physics. As one of the pioneering figures of the 20th century, Planck's ideas bridged the gap between the classical physics of the 19th century and the modern quantum mechanics that would dominate the 20th century. Yet, while his discoveries laid the foundation for the quantum revolution, Planck's personal experience with his own groundbreaking work is filled with complexity, hesitation, and philosophical struggle. His story is one of an intellectual battle between the old and the new, between classical and quantum thought, with far-reaching implications not only for science but also for how we understand the universe. At the dawn of the 20th century, classical physics was the prevailing paradigm, having successfully explained a wide array of natural phenomena. The theories of Newton and Maxwell governed our understanding of motion and electromagnetic fields. However, there were still unanswered questions, particularly regarding the nature of radiation emitted by heated objects, known as blackbodies. Classical physics, which had served scientists well for centuries, predicted that the intensity of radiation from a blackbody would increase indefinitely as the temperature rose, especially in the ultraviolet range. But when physicists began to measure the actual radiation emitted by blackbodies, they found that it did not follow the predictions of classical theory. This discrepancy, later dubbed the ultraviolet catastrophe, signaled that classical physics was inadequate for explaining the behavior of radiation at high temperatures. This problem became one of the most pressing issues in physics and required a radical rethinking of the laws of energy. Max Planck entered the scene at a crucial moment, attempting to solve this problem in 1900. His approach to blackbody radiation was both simple and revolutionary. Instead of assuming that energy was emitted or absorbed in a continuous manner, as classical physics suggested, Planck proposed that energy is emitted in discrete packets, or quanta. This was a profound departure from centuries of thought, where energy had been treated as continuous, like a flowing stream. Planck's idea, although initially conceived to address a specific problem, had far-reaching implications that would lay the foundation for the entire quantum theory. He introduced the Planck constant, a fundamental quantity that related the energy of a quantum to the frequency of radiation. This constant would later become one of the pillars of quantum mechanics and is still in use today. However, Planck himself did not immediately grasp the full significance of his discovery. For him, the concept of energy quanta was a mathematical tool, not a fundamental shift in how energy operated. Despite the success of his theory in solving the ultraviolet catastrophe, Planck struggled with the philosophical consequences of his work. The idea that energy could exist in discrete quantities was deeply unsettling to a scientist who had spent his career immersed in the continuous, deterministic world of classical physics. For Planck, the introduction of quanta was a temporary measure, a mathematical convenience that would eventually be replaced by a more complete classical theory. He did not see the concept of quantized energy as a profound reimagining of nature itself. Instead, Planck believed that the true nature of energy would eventually be explained in a way that restored the continuity of classical physics. This resistance to the radical implications of his own discovery reflects a larger theme in the history of science, the difficulty of letting go of established paradigms in the face of new, revolutionary ideas. The reluctance Planck felt in fully embracing the quantum revolution was not unique to him. Many of his contemporaries, including Albert Einstein and Niels Bohr, also struggled with the philosophical and conceptual implications of quantum mechanics. Einstein, for example, used Planck's ideas to explain the photoelectric effect, confirming the quantum nature of light, yet famously said, "God does not play dice with the universe," expressing his discomfort with the probabilistic nature of quantum theory. Similarly, Niels Bohr, who would go on to become one of the leading figures in the development of quantum mechanics, initially found the idea of a probabilistic universe unsettling. For these physicists, the transition from a deterministic to a probabilistic worldview was not just a scientific challenge but a philosophical one. Planck's hesitation is, therefore, part of a larger struggle within the scientific community during the early 20th century to come to terms with the radical implications of quantum mechanics. As the years passed, Planck's work began to take on greater significance. The quantum ideas that he had introduced were gradually expanded upon by scientists like Einstein, Bohr, and Heisenberg, who fully embraced the strange and counterintuitive nature of the quantum world. While Planck remained cautious about the philosophical implications of his discovery, his contributions provided the mathematical and conceptual framework that allowed quantum mechanics to flourish. The Planck constant, for example, became a cornerstone of quantum theory and is still used today in technologies such as semiconductors and lasers. Planck's role in the development of quantum mechanics is therefore immense, even though he did not fully embrace the theory in the same way as later physicists did. In conclusion, Max Planck's contributions to the birth of quantum mechanics are foundational. His solution to the ultraviolet catastrophe and the introduction of energy quanta changed the way scientists thought about energy and matter. However, Planck's personal struggle with his discovery highlights the intellectual challenges that accompany revolutionary scientific breakthroughs. The shift from classical to quantum physics was not merely a technical one, but also a philosophical revolution that forced scientists to rethink their entire view of the universe. Planck's hesitation to fully embrace the quantum revolution reflects the natural resistance to change that all great discoveries encounter. His legacy, however, is not only in the equations and constants he introduced, but also in his role as a pioneer who helped to usher in a new era of scientific understanding. The impact of his work is still felt today as quantum mechanics continues to shape both the direction of physics and the development of modern technologies. Max Planck's contributions to the field of physics were transformative, marking the beginning of the quantum revolution that would eventually alter the course of scientific thought forever. As one of the founders of quantum theory, Planck's insights not only solved long-standing problems in thermodynamics, but also opened new doors for understanding the fundamental nature of reality. His work on blackbody radiation and the concept of energy quanta laid the foundation for the field of quantum mechanics. However, Planck's story is not merely about scientific breakthroughs. It also reflects the intellectual struggles that accompany revolutionary ideas and the personal reservations that even the greatest scientists experience when faced with paradigm-shifting discoveries. At the end of the 19th century, classical physics seemed to be reaching its peak. The laws of motion, developed by Newton, and Maxwell's equations on electromagnetism provided a robust framework for understanding most natural phenomena. Yet, the behavior of radiation emitted by hot objects presented a significant puzzle. Classical theories predicted that the intensity of radiation from a black body would increase without limit as the temperature rose, particularly in the ultraviolet range. However, experiments contradicted these predictions, showing that the intensity of radiation reached a peak and then decreased at higher frequencies. This discrepancy, known as the ultraviolet catastrophe, posed a fundamental problem for classical physics and required a new theoretical approach. Max Planck entered the scene in 1900 with a solution that would change the course of physics. Rather than assuming that energy was emitted continuously, as classical physics had, Planck proposed that energy was emitted in discrete packets, or quanta. This insight was groundbreaking because it directly challenged the classical view that energy was a continuous variable. Planck's radiation law, which mathematically described the energy distribution of blackbody radiation, resolved the ultraviolet catastrophe and matched experimental data precisely. This was the beginning of quantum theory, and it introduced the concept of the Planck constant, a fundamental quantity that linked energy and frequency. Despite the success of his radiation law, Planck did not initially realize the full implications of his discovery. He saw the idea of energy quanta as a mathematical tool, a convenience to solve a particular problem in radiation theory, not as a new way of understanding energy itself. For Planck, the concept of quanta was a temporary fix. He believed that future developments in classical physics would eventually provide a more complete and continuous explanation. His reluctance to fully embrace the quantum nature of energy highlights the tension between established scientific paradigms and the radical ideas that sometimes emerge to challenge them. Planck's hesitation was not unique to him. Many of his contemporaries also grappled with the implications of quantum mechanics. Albert Einstein, for example, applied the concept of quanta to explain the photoelectric effect, but even he was uneasy with the probabilistic nature of quantum theory. In his famous statement, "God does not play dice with the universe," Einstein expressed his discomfort with the idea that fundamental processes could be governed by probability rather than determinism. Similarly, Niels Bohr, who would become one of the central figures in the development of quantum mechanics, initially struggled with the implications of the theory. The transition from classical to quantum physics represented not just a scientific revolution but also a philosophical shift, one that forced scientists to reconsider their understanding of the universe itself. As time passed, however, the significance of Planck's discovery became clearer. The concept of quanta was expanded upon by physicists like Einstein, Bohr, and Heisenberg, who fully embraced the quantum worldview. Planck's initial reluctance to accept the full implications of his work did not diminish its importance. His introduction of the Planck constant and the idea that energy is quantized laid the groundwork for quantum mechanics, which would go on to revolutionize physics and lead to the development of technologies such as semiconductors, lasers, and quantum computing. Planck's work provided the mathematical and conceptual framework that enabled later scientists to develop a more complete theory of the quantum world. In the years following his discovery, Planck gradually came to recognize the revolutionary nature of his work. Though he never fully embraced the probabilistic nature of quantum mechanics, he acknowledged the importance of his contribution and the way it had shaped the future of physics. His role in the development of quantum theory is often understated, but his work was pivotal in laying the foundation for the quantum revolution. Planck's legacy is not just in the equations he developed or the ideas he proposed, but also in the way his work helped to usher in a new era of scientific discovery, one that continues to shape our understanding of the microscopic world. Max Planck's journey through the quantum revolution reflects both the excitement and the uncertainty that accompany scientific breakthroughs. His initial hesitation to embrace the quantum nature of energy highlights the intellectual struggle that many scientists face when confronted with ideas that challenge established thought. Planck's contributions to quantum mechanics paved the way for the later developments of the field, but his story also serves as a reminder of how difficult it can be to let go of old paradigms and embrace new, radically different ideas. His work in the early 20th century helped to shape the future of physics, and its impact can still be felt today in the technologies and discoveries that continue to emerge from the quantum world. Planck's legacy is a testament to the power of intellectual curiosity and the courage required to challenge the conventional wisdom of the time. Max Planck's contributions to modern physics stand as a testament to the power of scientific inquiry and intellectual courage. His discovery of the quantization of energy, which led to the development of quantum theory, reshaped the way we understand the universe. While Planck is often celebrated for his pioneering work on blackbody radiation, his story is also one of intellectual conflict, philosophical hesitation, and an evolving understanding of his own discoveries. The complexity of his work provides an essential insight into how scientific revolutions unfold, often in unexpected and reluctant ways. At the close of the 19th century, physics was at a turning point. Classical theories, primarily rooted in the laws of Newtonian mechanics and Maxwell's equations, had successfully explained most physical phenomena. However, a significant gap existed in explaining the radiation emitted by heated objects, specifically blackbodies. Classical physics predicted that as the temperature of a blackbody increased, the intensity of radiation emitted would increase indefinitely at shorter wavelengths, particularly in the ultraviolet range. Yet experimental data contradicted this, revealing a drop-off in radiation intensity at higher frequencies. This discrepancy, known as the ultraviolet catastrophe, presented a significant challenge to the classical understanding of energy and required a new theoretical approach. In 1900, Planck addressed this issue with a solution that would become one of the cornerstones of modern physics. His insight was deceptively simple. Energy is not emitted or absorbed continuously, as classical physics had assumed, but in discrete packets called quanta. This idea was groundbreaking, as it directly challenged the classical view of a continuous flow of energy. Planck's radiation law, which described the distribution of radiation emitted by a blackbody, matched experimental data and solved the ultraviolet catastrophe. His introduction of the Planck constant provided a crucial link between energy and frequency, setting the stage for the development of quantum mechanics. Despite the success of his mathematical model, Planck was initially reluctant to embrace the full implications of his discovery. For him, the concept of quanta was merely a mathematical tool designed to solve a specific problem in radiation theory, not a fundamental change in our understanding of energy. Planck believed that his approach was temporary, a way to fix an anomaly in classical physics, and he expected that a more complete theory would eventually replace it. This reluctance to fully accept the quantum nature of energy highlights the tension between classical and emerging quantum thought. For Planck, the idea that energy was quantized was a difficult pill to swallow, as it contradicted the continuous nature of energy that had been so central to classical physics. This internal conflict in Planck's thinking is not unique to him. Many of the early pioneers of quantum mechanics, such as Albert Einstein and Niels Bohr, faced similar challenges in accepting the full implications of quantum theory. Einstein, despite his confirmation of Planck's quanta through his explanation of the photoelectric effect, was uncomfortable with the probabilistic nature of quantum mechanics. His famous statement, "God does not play dice with the universe," expressed his reluctance to accept the randomness and uncertainty that quantum theory introduced into the understanding of physical reality. Similarly, Bohr and others who advanced the quantum theory struggled with the philosophical implications of a world governed by uncertainty and probability rather than determinism. While Planck was hesitant to embrace the broader consequences of quantum theory, his work was instrumental in laying the foundation for later developments. Planck's radiation law and the introduction of the Planck constant provided the mathematical framework upon which Einstein, Bohr, and Heisenberg would build the more comprehensive quantum theory. Despite his personal reservations, Planck's contribution opened the door for new scientific paradigms, fundamentally changing the course of physics. Quantum mechanics, as it developed, revealed a world of bizarre phenomena where particles could exist in multiple states at once, where uncertainty was a fundamental property, and where observation itself could affect the state of a system. Planck's role in the development of quantum mechanics is both pivotal and complex. He set the stage for the quantum revolution, yet his reluctance to fully embrace the quantum nature of the universe highlights the difficult transition from classical to quantum thinking. Even as Planck's ideas were crucial in the development of the quantum theory, his cautious approach to their implications is a reminder of the resistance that new ideas often face, even from their creators. Planck's story is one of intellectual courage, but it is also one of hesitation, a reflection of the internal conflict that often accompanies groundbreaking discoveries. Ultimately, Max Planck's legacy is not just in the discoveries he made, but in the way his work helped to pave the way for the scientific revolutions that followed. His introduction of the Planck constant and the idea of energy quanta formed the cornerstone of quantum mechanics. His cautious acceptance of the full implications of his work shows the intellectual struggle that great scientists face when confronting ideas that challenge long-held beliefs. Planck's contributions to quantum theory helped reshape our understanding of the universe, and his role in this transformation will continue to inspire generations of scientists. His story is a testament to the complex and often difficult process of scientific discovery, where new ideas must challenge and ultimately replace old paradigms to bring us closer to understanding the true nature of reality.